The River of Time, a cosmic journey through the fourth dimension. In the vast cathedral of existence, where galaxies spin like distant prayer wheels and stars breathe light across impossible distances, there flows a river unlike any other, the River of Time itself. This is not the familiar time of human clocks and calendars, but something far more profound. The fourth dimension that weaves through every particle of creation, the invisible thread upon which the entire tapestry of reality hangs. Time, in the cosmic sense, is not merely the backdrop against which events unfold. It is an active participant in the grand choreography of existence, bending and flowing, stretching and contracting, carrying within its current the very essence of what was, what is, and what shall be. From the first moment of the Big Bang, when time itself sprang into being alongside space, to the distant future when galaxies will drift so far apart that their light can no longer bridge the growing darkness between them. This fourth dimension shapes every aspect of the universe's story. Tonight, as consciousness prepares for its own journey into the timeless realm of sleep, let awareness drift along this cosmic river. Here, in the gentle flow of cosmic time, the mind can find a peace that transcends the urgency of earthly hours and minutes. In understanding how time moves through the universe, how it slows near massive objects, how it carries the arrow of complexity from simple to profound. Perhaps the restless thoughts of the day can settle into the deeper rhythms that govern all existence. This is an invitation to swim in waters older than worlds, to float upon currents that began nearly 14 billion years ago and will continue long after the last star has faded to darkness. Chapter 1. The Birth of Moments. In the beginning, there was no beginning. The very concept of before dissolves into meaninglessness when contemplating the origin of time itself. For without time, there can be no sequence, no causation, no before or after. Yet from this impossible starting point, or perhaps more accurately, from the absence of any starting point at all, the universe began its first and most miraculous act, the simultaneous creation of space and time. Around 13,800,000,000 years ago, though even this number struggles to capture something that predates the very existence of years, the Big Bang initiated not just the expansion of space, but the flowing of time. In that first inconceivable instant, duration itself came into being. The fourth dimension unfurled like a flower blooming in fast motion, creating the framework within which all future moments would find their place. This birth of time was not gentle. In the first fraction of a second, a period so brief that human language has no adequate terms to describe it, the universe underwent transformations more dramatic than anything that would ever happen again. Time moved differently then, compressed and intense, each Planck-length moment containing changes that would later require millennia to accomplish. The fundamental forces that govern reality separated from their unified origin, like streams branching from a single spring, each carrying its own current of temporal possibility. The cosmic microwave background radiation, that ancient light which still bathes the universe in the faint afterglow of creation, carries within its gentle warmth the memory of time's earliest moments. When this radiation finally broke free from the primordial plasma, around 380,000 years after the initial expansion began, it marked not just the universe becoming transparent to light, but time reaching a new maturity. The cosmos had developed enough complexity to support the kind of time that modern physics recognizes, the flowing duration that allows cause to precede effect, that permits the gradual assembly of atoms from their component parts. Within this newborn time, The first hydrogen nuclei formed as protons and neutrons found each other in the cooling cosmic soup. These simple marriages of particles represented time's first great creative act, the transformation of energy into matter stable enough to persist across cosmic ages. Each hydrogen nucleus was a tiny clock, its internal structure marking duration through the probability waves of quantum mechanics, its very existence proving that time had become sophisticated enough to support lasting form. The universe during these early epochs was smaller, denser, and hotter than the human mind can easily comprehend. Yet even in this exotic environment, time flowed with the same essential character it possesses today. Seconds passed into minutes, minutes into hours, hours into years, as the cosmos gradually cooled and expanded. The rate of this cooling followed mathematical laws as precise as any earthly timepiece, with temperature dropping according to equations that describe the relationship between time and cosmic expansion. As the universe aged through its first million years, time itself was learning how to carry the growing complexity that would eventually lead to stars, planets, and life. The Dark Ages had begun, a period when no stars yet shone to mark the passage of time with their light, when only the cosmic microwave background provided illumination. Yet even in this darkness, time was working, allowing gravity to gather the nearly uniform distribution of matter into the first subtle clumps that would eventually become the seeds of galaxies. During this ancient epoch, time moved with a patience that dwarfs human comprehension. Millions of years passed like moments in the cosmic timeline, each century a barely perceptible tick in the grand clock of existence. The universe was preparing for its next great temporal milestone, the moment when gravity would compress the first clouds of hydrogen and helium to the point where nuclear fusion could begin, creating the first stars and, with them, the first cosmic lighthouses to illuminate time's passage. Now, close your eyes and picture how all of this might look. The universe in its infancy, time itself taking its first tentative steps, duration learning how to support the slow dance of particles coming together in the cooling cosmic darkness. Chapter 2: The Curvature of Duration. As the universe matured and the first stars ignited their nuclear fires, time began to reveal one of its most profound secrets: its intimate relationship with space, matter, and gravity. What humans experience as the steady, uniform flow of seconds and minutes is, from the cosmic perspective, far more fluid and malleable than earthly intuition suggests. Time, it turns out, is not the rigid framework that early scientists imagined, but something that bends and stretches like a river changing course around obstacles in its path. This discovery emerged from the mathematical poetry of Einstein's general relativity, which revealed that massive objects create curves in the fabric of space-time itself. Near a star, time flows slightly slower than in the empty spaces between stars. Near a planet, time moves differently than in the void. Near a black hole, time can slow to such an extent that what appears to be eternal from one perspective can be mere moments from another. The universe, it became clear, contains not one uniform time but countless local times, each flowing at its own rate according to the gravitational environment in which it finds itself. Consider the elegant dance of time around a neutron star, where matter has been compressed to densities so extreme that a teaspoon of its substance would weigh as much as a mountain. Here, time moves noticeably slower than in the regions of space between stars. An observer watching from a safe distance would see events on the neutron star's surface unfolding in slow motion, like a film played at half speed. Yet for any hypothetical observer on the neutron star itself, time would seem to flow normally. It is only in comparison, only in the relationship between different regions of space-time, that the flexibility of duration becomes apparent. This warping of time reaches its most extreme expression in the vicinity of black holes, those cosmic regions where matter has collapsed so completely that space-time itself tears like fabric stretched beyond its breaking point. At the event horizon of a black hole, time comes nearly to a stop from the perspective of distant observers. Light itself struggles against the immense gravitational field, its usual swift journey stretched into an eternal crawl. Yet this is not a stopping of time in any absolute sense, but rather a relationship between different temporal reference frames, each equally valid from the perspective of physics. The cosmic implications of time's curvature extend far beyond individual stars and black holes. Entire galaxies warp space-time on scales almost impossible to visualize, creating vast regions where time flows in subtly different ways. The Milky Way galaxy, that great spiral of stars that contains the solar system, sits within its own temporal environment, its collective mass creating a gentle but measurable difference in the flow of time compared to the intergalactic void. Clocks in different parts of the galaxy, if they could somehow be compared directly, would show minute but real discrepancies in their measurement of duration. On the largest scales, the expansion of the universe itself creates temporal effects that shape the cosmic story. Space-time stretches between galaxies, carrying them apart at rates that increase with distance. This expansion means that time itself is distributed differently across cosmic distances, with the most distant galaxies existing in temporal relationships so complex that the light now arriving at modern telescopes left its source when the universe was young and time flowed according to different rules. The cosmic microwave background radiation provides a kind of universal timekeeper, a reference frame against which the warping effects of local gravity can be measured. This ancient light, cooled and redshifted by billions of years of cosmic expansion, carries within its subtle variations the signatures of gravitational time dilation from the early universe. In its gentle glow, astronomers can read the history of how time has flowed differently in different regions of space throughout cosmic history. Galaxy clusters, those vast congregations of hundreds or thousands of galaxies bound together by gravity, create time environments so complex that they challenge human ability to visualize. Within these clusters, space-time is warped by the combined mass of countless stars, planets, and dark matter, creating regions where time flows at subtly different rates depending on position. The cosmic web itself, that grand structure of filaments and voids that organizes matter on the largest scales, is also a web of temporal relationships, with time flowing differently along the dense filaments than in the empty voids between them. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. Chapter 3. The Great Unfolding. Within the curved space-time of the expanding universe, cosmic history unfolds not as a simple sequence of events, but as a grand symphony of temporal development, each epoch building upon the last in a progression from simplicity toward ever greater complexity. This cosmic evolution follows what scientists call the arrow of time, a fundamental direction built into the structure of reality itself, pointing always from the ordered toward the less ordered, from the simple toward the complex, from the potential toward the actual. The first movement of this cosmic symphony began in the initial moments after the Big Bang, when the universe existed in a state of almost perfect smoothness and simplicity. The The cosmic microwave background reveals this ancient perfection in its nearly uniform temperature across the entire sky, interrupted only by tiny fluctuations that represent the seeds of all future complexity. These minute variations in density and temperature, smaller than 1 part in 100,000, carried within them the potential for everything that would later emerge: galaxies, stars, planets, and life itself. As cosmic time advanced through its first hundreds of millions of years, gravity began the slow work of amplifying these tiny differences. Regions that were slightly denser than average attracted more matter to themselves, gradually growing larger and more distinct from their surroundings. This process, known as gravitational collapse, represents one of time's most important creative mechanisms: the ability to transform small differences into large structures through the patient accumulation of change. The dark ages of the universe, lasting from the recombination epoch until the formation of the first stars, were not truly dark from the perspective of cosmic development. During this period, invisible dark matter was assembling itself into the vast scaffolding that would eventually support visible galaxies. Time was working invisibly, building structures that could not yet be seen, but would prove essential for everything that followed. The cosmic web began to take shape during these seemingly empty eons, as dark matter flowed along the paths of least resistance through the expanding spacetime, creating filaments and nodes that would later become the sites of galaxy formation. When the first stars finally ignited, around 100 to 200 million years after the Big Bang, they marked a new phase in time's creative power. These ancient suns were different from modern stars, larger, hotter, and shorter-lived, composed almost entirely of hydrogen and helium, with virtually none of the heavier elements that would later make planets and life possible. Yet their brief, violent lives served time's arrow by creating and dispersing the first carbon, oxygen, silicon, and iron atoms, the building blocks of chemical complexity. The death of these first stars in spectacular supernovae represented time's first great acts of cosmic alchemy. In the intense pressures and temperatures of stellar collapse, the simple hydrogen and helium of the early universe were forged into the entire periodic table of elements. Time carried these newly created atoms across space in the shock waves of exploding stars, seeding the universe with the materials necessary for the formation of rocky planets and, eventually, life itself. As cosmic time advanced through its first billion years, the universe began to develop the hierarchical structure visible today. Small galaxies formed first, then merged and grew into larger systems. Galaxy clusters assembled from the gravitational attraction of individual galaxies. The cosmic web took on its modern appearance, with vast filaments of dark matter and gas connecting dense nodes where galaxy clusters formed. Throughout this process, time's arrow pointed steadily from the simple toward the complex, from the uniform toward the diverse, from the potential toward the realized. The formation of the first planetary systems marked another crucial milestone in cosmic development. As second and third generation stars formed from gas clouds enriched with heavy elements from earlier stellar generations, rocky planets began to condense from the leftover material. These worlds provided new environments where time could experiment with different forms of organization and complexity. The chemical evolution that led to life represents time's most remarkable creative achievement: the emergence of systems capable of growth, reproduction, and adaptation. On Earth, time's creative power reached new heights with the emergence of life around 4 billion years ago. Living systems represent a unique form of temporal organization, capable of maintaining complex structures through the constant flow of energy and matter. Life harnesses time's arrow for its own purposes, using the tendency toward increasing entropy to drive the processes of growth and reproduction. In living systems, time becomes not just the medium through which change occurs, but an active participant in the creation and maintenance of complexity. The evolution of life over cosmic time demonstrates the arrow of time operating on multiple scales simultaneously. While individual organisms age and die, increasing in entropy according to the second law of thermodynamics, populations evolve and become more complex over millions of years. This apparent contradiction resolves when viewed from the cosmic perspective. Local decreases in entropy are possible as long as they are more than compensated by increases elsewhere in the system. Now, close your eyes and picture how all of this might look. The universe growing more complex with each passing eon, time itself acting as a sculptor, gradually carving intricate structures from the simple clay of hydrogen and helium. Chapter 4. The Rhythm of Stars. In the cosmic orchestra of time, stars serve as both musicians and metronomes, their nuclear fires marking the passage of cosmic epochs, while their life cycles create the rhythm that drives the universe's ongoing evolution. Each star exists within its own temporal environment, living and dying according to laws that connect the quantum realm of atomic nuclei to the vast scales of galactic time. The birth, life, and death of stars represent time's most visible creative process, transforming the simple elements of the early universe into the complex chemistry that makes planets and life possible. The formation of a star begins in the slow dance of gravitational collapse, as vast clouds of gas and dust gradually contract under their own weight over millions of years. Time moves with infinite patience during this process, allowing gravity to overcome the thermal motion of individual gas molecules and slowly draw them together. Within these stellar nurseries, time operates on multiple scales simultaneously. The rapid motion of individual atoms, the slower circulation of turbulent gas flows, and the stately progression of gravitational collapse that spans geological ages. When a protostar finally reaches the critical temperature and pressure necessary for nuclear fusion to begin, time undergoes a fundamental transition. The chaotic gravitational collapse gives way to the stable rhythm of nuclear burning, as hydrogen nuclei fuse into helium in a process so steady and predictable that stars can maintain it for billions of years. This nuclear heartbeat represents one of time's most reliable clockwork mechanisms, with each fusion reaction releasing energy at rates governed by the fundamental constants of physics. The lifetime of a star depends intimately on its mass, creating a cosmic relationship between space and time that shapes the evolution of entire galaxies. The most massive stars burn through their nuclear fuel in just a few million years, their intense gravity compressing matter to such extreme densities that fusion proceeds at tremendous rates. These stellar giants live fast and die young, exploding as supernovae while the universe is still relatively young. Their brief but brilliant lives seed space with heavy elements, while their deaths trigger the formation of new stars in nearby gas clouds. Smaller stars, like the Sun, burn their nuclear fuel more conservatively, maintaining steady fusion for billions of years. These stellar marathon runners provide the stable energy sources necessary for planetary systems to develop and evolve over cosmic time. Their steady light creates the temporal frameworks within which planets can maintain liquid water, develop atmospheres, and support the chemical processes that lead to life. The Sun's nuclear burning represents a clock so reliable that life on Earth has evolved to depend on its rhythms across geological time. The smallest stars, red dwarfs with masses less than half that of the Sun, burn so slowly that they can maintain nuclear fusion for trillions of years, longer than the current age of the universe. These cosmic misers will continue shining long after more massive stars have exhausted their fuel and died, providing the last sources of stellar energy in a universe growing cold and dark through expansion. In the far future, red dwarfs will serve as the final lighthouses of cosmic time, marking the passage of eons in a universe growing ever more empty and silent. The death of stars creates some of time's most dramatic events, as gravitational collapse compresses matter to densities where normal physics breaks down and exotic states emerge. When a massive star reaches the end of its nuclear fuel, gravity overwhelms all other forces and triggers a core collapse so rapid that it represents one of the fastest processes in the known universe. In less than a second, the star's core contracts from the size of Earth to a sphere only 20 kilometers across, creating densities comparable to those found in atomic nuclei. This stellar collapse creates neutron stars, objects so dense that time itself behaves differently on their surfaces. A neutron star's immense gravitational field slows time relative to observers in weaker gravitational environments, creating a cosmic laboratory where the relationship between matter, energy, and time can be studied in its most extreme form. Pulsars, rapidly spinning neutron stars that emit beams of radiation, serve as cosmic lighthouses whose precisely timed pulses can be detected across vast distances, providing astronomers with some of the most accurate clocks in the universe. The most massive stars die in explosions so violent that they create black holes, regions where matter becomes so dense that space-time curves back on itself and time appears to stop from the perspective of distant observers. These cosmic endpoints represent time's ultimate boundary, places where the normal flow of duration encounters the limits of physical law. Yet even black holes exist within cosmic time, slowly evaporating through Hawking radiation over periods so vast that they make the current age of the universe seem like an instant. Binary star systems create their own complex temporal relationships, as two stars orbit each other in gravitational dances that can last for billions of years. When both stars are similar in mass, they evolve together, their nuclear burning synchronized by their mutual gravitational influence. When one star is much more massive than the other, it evolves more rapidly, sometimes transferring matter to its companion and creating exotic systems where time flows according to the complex interplay of gravity, nuclear physics, and stellar evolution. The formation of planetary systems around stars creates new temporal environments where cosmic time intersects with geological time. Rocky planets develop their own internal clocks as radioactive elements decay and create heat, driving geological processes that operate on timescales ranging from seconds to billions of years. The presence of planets also affects stellar evolution, as tidal forces and magnetic interactions create subtle changes in stellar rotation and nuclear burning rates. Chapter 5: The Gardens of Gravity. Within the vast architecture of cosmic time, gravity serves as the master gardener, cultivating structures of ever-increasing complexity across scales that span from individual stars to the largest observable features of the universe. This gravitational cultivation operates through time with a patience that exceeds human comprehension, slowly gathering matter into the hierarchical patterns that give the cosmos its current form. From the perspective of the fourth dimension, gravity and time work in partnership, with gravity providing the organizing force and time providing the medium through which organization can develop and persist. The cosmic web represents gravity's grandest gardening project, a vast network of dark matter filaments that serves as the scaffolding for all visible structure in the universe. This web took shape over billions of years as gravity amplified the tiny density fluctuations present in the early universe, gradually creating a foam-like pattern of dense filaments surrounding vast empty voids. Time was essential to this process, providing the long durations necessary for gravity's weak but persistent influence to accumulate small differences into large-scale structures. Along the filaments of the cosmic web, gravity creates special temporal environments where matter flows like water, finding the path of least resistance. Gas clouds stream along these invisible highways, guided by gravitational fields that channel them toward the nodes where galaxies form. This process demonstrates time's role as an active participant in cosmic evolution. Without sufficient duration, gravity could never gather enough material to create the dense concentrations necessary for star formation and galactic development. Galaxy formation represents one of time's most complex creative processes, involving the coordinated interaction of dark matter, ordinary matter, magnetic fields, and stellar feedback across hundreds of millions of years. The first small galaxies formed when the universe was less than 1 billion years old, as gravity concentrated matter in the deepest wells of the cosmic web. These early systems were irregular and chaotic, lacking the elegant spiral and elliptical shapes that characterize mature galaxies today. The evolution of galaxies over cosmic time demonstrates gravity's ability to create order from chaos through patient accumulation of change. Spiral galaxies develop their graceful arms through density waves that propagate through stellar disks over hundreds of millions of years, creating the conditions for star formation in regular patterns. Elliptical galaxies achieve their smooth, rounded shapes through the gravitational mixing that occurs when smaller galaxies merge and lose their individual identities in the cosmic equivalent of rivers flowing together. The supermassive black holes that lurk at the centers of most galaxies represent gravity's most extreme expression, creating regions where time becomes so severely warped that normal causality breaks down. These cosmic monsters, containing millions or billions of times the mass of the Sun, demonstrate gravity's ability to create temporal environments unlike anything else in the universe. Near the event horizon of a supermassive black hole, time slows to such an extent that processes which would take seconds in normal space-time can appear to take millennia from the perspective of distant observers. The relationship between supermassive black holes and their host galaxies reveals a deep connection between gravity's organizing power and time's creative potential. These massive objects regulate star formation throughout their galaxies by heating and dispersing the gas clouds that would otherwise collapse to form new stars. This feedback mechanism operates over cosmic time, creating a self-regulating system where galaxies and their central black holes evolve together in a gravitational partnership that spans billions of years. Galaxy clusters, the largest gravitationally bound structures in the universe, represent gravity's ability to organize matter on scales approaching the cosmic horizon itself. These vast assemblages contain hundreds or thousands of individual galaxies, along with enormous quantities of hot gas and dark matter, all held together by gravitational fields so strong that they bend light and create cosmic lenses that distort the images of more distant galaxies. The formation of galaxy clusters required the entire age of the universe, as gravity slowly accumulated matter across the largest scales where its influence can overcome cosmic expansion. The hot gas that fills galaxy clusters creates its own temporal environment, heated to temperatures of millions of degrees by the gravitational energy released during cluster formation. This gas radiates X-rays that carry information about the cluster's gravitational field and thermal history, allowing astronomers to study how gravity has shaped the evolution of cosmic structure over time. The X-ray emission serves as a clock, marking the passage of time through the gradual cooling and chemical enrichment of the cluster gas. Dark matter, the invisible substance that comprises most of the universe's mass, plays a crucial role in gravity's partnership with time. Dark matter feels only gravitational force, allowing it to respond purely to the geometric curvature of spacetime without the electromagnetic interactions that complicate the behavior of ordinary matter. This simplicity enables dark matter to create the clean gravitational scaffolding upon which ordinary matter can organize itself into stars, galaxies, and larger structures. The interplay between dark matter and ordinary matter creates complex temporal relationships that operate on multiple scales simultaneously. While dark matter provides the long-term gravitational framework for structure formation, ordinary matter responds to shorter-term processes like stellar feedback, supernovae, and black hole activity. These different timescales interact to create the rich variety of cosmic structures observed today, from the smooth, dark matter halos that surround galaxies to the complex star formation patterns within galactic disks. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. Now, close your eyes and picture how all of this might look. Gravity working through cosmic time like an infinite sculptor, slowly shaping the universe into patterns of increasing beauty and complexity. Chapter 6. The Memory of Light. Light serves as the universe's memory, carrying information across cosmic distances and through cosmic time with a fidelity that preserves the history of everything it has encountered along its journey. Photons born in the nuclear furnaces of distant stars, in the accretion disks of black holes, or in the primordial fireball of the Big Bang itself, travel through space-time as messengers from the past, delivering their cargo of information to any observer capable of receiving it. From the perspective of the fourth dimension, light creates a bridge between different moments in cosmic history, allowing the present to directly observe and study the deep past. The cosmic microwave background represents the universe's oldest preserved memory, a photograph of the cosmos taken when it was only 380,000 years old. This ancient light carries within its gentle glow the imprint of physical conditions from an era when the universe was hot, dense, and fundamentally different from today. The slight temperature variations observed in this background radiation reveal the seeds of all later cosmic structure. The tiny density fluctuations that gravity would amplify over billions of years into the galaxies, clusters, and cosmic web observed today. When modern telescopes detect this primordial radiation, they are performing a form of time travel, observing the universe as it existed when atoms first formed and space became transparent to light. The photons arriving today began their journey across space-time when the cosmos was 1,000 times smaller and 1 billion times denser than it is now. These ancient messengers have traveled for nearly 14 billion years, their wavelengths stretched by cosmic expansion until radiation that was once visible light has become microwave radiation detectable only by specialized instruments. The light from distant galaxies provides windows into cosmic history at different epochs, with more distant objects appearing as they existed when the universe was younger. The most distant galaxies visible to modern telescopes appear as they were when cosmic time had advanced only a few 100 million years beyond the Big Bang, showing star formation proceeding in environments very different from the local universe. These early galaxies were smaller, more irregular, and more actively forming stars than their modern counterparts, preserving in their light the memory of cosmic adolescence. Quasars, the brilliant beacons powered by supermassive black holes consuming matter at tremendous rates, serve as cosmic lighthouses whose emission can be detected across most of the observable universe. The light from the most distant quasars began its journey when the universe was less than 1 billion years old, carrying information about the early growth of supermassive black holes and the formation of the first massive galaxies. This ancient light reveals that black holes weighing billions of times the mass of the Sun somehow formed very early in cosmic history, presenting puzzles about rapid growth in the early universe that astronomers are still working to solve. The absorption lines visible in the spectra of distant quasars create a form of cosmic archaeology, revealing the properties of gas clouds encountered during the light's journey across space and time. Each absorption feature represents matter at a different distance and therefore a different moment in cosmic history, allowing astronomers to study the chemical evolution of the universe and the gradual enrichment of intergalactic space with heavy elements produced in stars. This technique transforms distant quasars into cosmic searchlights, illuminating the otherwise invisible matter that fills the space between galaxies. Supernovae serve as cosmic candles, whose brightness can be used to measure distances and trace the expansion history of the universe. Type Ia supernovae, produced when white dwarf stars accumulate matter from companion stars until they explode in thermonuclear detonations, achieve remarkably similar peak brightnesses that make them excellent standard candles for cosmic distance measurement. The light from these stellar explosions carries information about the rate of cosmic expansion at the time when each supernova occurred, allowing astronomers to trace how expansion has changed over cosmic time. The discovery that distant supernovae appear fainter than expected for their redshifts led to the revolutionary conclusion that cosmic expansion is accelerating rather than slowing down as previously thought. This acceleration implies the existence of dark energy, a mysterious component that comprises most of the universe's energy density and drives space-time to expand at an ever-increasing rate. The light from ancient supernovae thus revealed one of the most profound discoveries in modern cosmology, showing that the universe's expansion history is more complex than anyone had imagined. Gravitational lensing creates another form of cosmic memory, as the light from distant objects is bent and distorted by the gravitational fields of intervening matter. Massive galaxy clusters can act as cosmic telescopes, magnifying and distorting the images of more distant galaxies in ways that reveal both the mass distribution of the lensing cluster and the properties of the background sources. This gravitational focusing effect allows astronomers to study galaxies so distant and faint that they would otherwise be undetectable, extending the observable reach of cosmic memory deeper into the past. The time delay between multiple images of gravitationally lensed quasars provides a direct measurement of cosmic distances and expansion rates. When a quasar's brightness varies, the changes appear at different times in the multiple lensed images because the light paths have different lengths. These time delays depend on the geometry of space-time and the expansion rate of the universe, allowing astronomers to measure cosmic parameters independently of other methods. The light itself becomes a cosmic clock, measuring time differences that reveal the fundamental properties of space-time. Neutrinos, ghostly particles that interact so weakly with matter that they can travel through entire planets without being absorbed, carry their own form of cosmic memory. Neutrinos from the Sun arrive at Earth just 8 minutes after being produced in nuclear reactions, providing real-time information about solar nuclear burning. Neutrinos from supernovae can reach Earth hours before the light from the same explosion, offering the first warning of stellar death and carrying information about the extreme physics of stellar core collapse. The cosmic neutrino background, predicted to exist as a relic of the early universe similar to the cosmic microwave background, carries memory from an even earlier epoch when the universe was only a few seconds old. These primordial neutrinos have never been directly detected due to their extremely low energies, but their existence and properties provide crucial information about the early universe and the physics of the Big Bang. Future experiments may eventually detect this relic neutrino radiation, opening another window into cosmic memory from the universe's first moments. Chapter 7: The Pulse of Existence. Deep within the architecture of cosmic time, certain celestial objects serve as natural timepieces, their regular pulsations marking the passage of duration with precision that rivals the most accurate human-made clocks. These cosmic chronometers, born from the extreme physics of stellar death and gravitational collapse, create rhythms that span scales from microseconds to millennia, each beat carrying information about the fundamental nature of matter, energy, and space-time itself. In their steady pulsing, the universe reveals its most intimate relationship with time, showing how duration emerges from the quantum realm and propagates across cosmic distances. Pulsars represent time's most precise natural expression, neutron stars spinning at rates that can exceed 600 rotations per second while maintaining accuracy comparable to atomic clocks. These stellar remnants, compressed to densities where matter exists in forms found nowhere else in the universe, emit beams of radiation that sweep across space like cosmic lighthouses. Each pulse represents a complete rotation of a star so dense that a teaspoon of its material would weigh as much as a mountain, creating temporal precision from gravitational collapse and conservation of angular momentum. The formation of a pulsar begins in the violent death of a massive star, when gravitational collapse compresses the stellar core to nuclear density in less than a second. This catastrophic event represents one of the fastest processes in cosmic physics, as matter transitions from normal atomic structure to a state where protons and electrons are crushed together to form neutrons. The resulting neutron star inherits the angular momentum of its much larger progenitor, but conservation laws require this rotation to speed up dramatically as the radius shrinks. Like an ice skater pulling in their arms during a spin, young pulsars rotate with such stability that their pulse periods can be measured to 15 decimal places, making them among the most precise clocks in the known universe. This extraordinary accuracy allows astronomers to detect minute changes in pulse timing caused by gravitational waves, planetary companions, or the pulsar's motion through space. The timing of pulsar signals has confirmed some of the most subtle predictions of Einstein's general relativity, including the energy loss from binary systems due to gravitational wave emission. Millisecond pulsars, ancient neutron stars, spun up to incredible rotation rates by mass transfer from companion stars, maintain their rapid spinning for billions of years with timing stability that exceeds most terrestrial clocks. These cosmic metronomes rotate hundreds of times per second while drifting by only microseconds over periods of many years. Their extraordinary stability makes them valuable tools for detecting gravitational waves, testing theories of gravity, and potentially serving as natural GPS systems for spacecraft navigating the outer solar system. The discovery of the first binary pulsar provided direct evidence for gravitational waves decades before their detection by ground-based interferometers. The orbital decay of this system, as the two neutron stars spiral inward while losing energy to gravitational radiation, matches Einstein's predictions with remarkable precision. Time itself becomes visible in this system, as the gradual decrease in orbital period marks the conversion of gravitational potential energy into ripples in space-time that propagate outward at the speed of light. Variable stars create longer temporal rhythms, with pulsation periods ranging from hours to years as these stellar giants expand and contract under the influence of their own radiation pressure. Cepheid variables, with their characteristic sawtooth light curves, serve as cosmic distance indicators because their pulsation periods are directly related to their intrinsic luminosities. The time signature of each Cepheid's pulsation carries information about stellar structure and evolution, while their brightness variations provide one of the primary tools for measuring distances to nearby galaxies. RR Lyrae stars, older and less massive than Cepheids, create their own temporal patterns with periods measured in hours rather than days. These ancient stars, found primarily in globular clusters and stellar halos, pulsate as they burn helium in their cores during a brief but distinctive phase of stellar evolution. Their light curves serve as fossil records of stellar ages, carrying information about the early history of galaxy formation encoded in the timing of their variability. Long-period variables, including Mira-type stars that can change brightness by factors of thousands over periods of months to years, demonstrate how stellar evolution creates complex temporal relationships between nuclear burning, stellar structure, and mass loss. These aging giants pulsate with periods that slowly change over decades as their internal structure evolves, creating temporal signatures that reveal the physics of stellar atmospheres and the process by which stars return processed material to the interstellar medium. Eclipsing binary systems create another form of cosmic timekeeping, as the orbital motion of two stars creates regular dimming events when one star passes in front of the other. These stellar clockwork mechanisms can maintain their rhythms for millions of years, with eclipse periods ranging from hours for close binaries to decades for widely separated systems. The precise timing of these eclipses reveals intimate details about stellar masses, radii, and orbital evolution, while their long-term stability demonstrates how gravitational dynamics create temporal order from the chaos of stellar formation. Some binary systems exhibit more complex temporal behavior, with orbital periods that change over time due to mass transfer, tidal interactions, or the presence of additional companions. These systems create temporal patterns within patterns, like nested rhythms in a cosmic symphony. The interplay between different timescales, orbital periods, stellar evolution, and mass transfer rates creates a rich temporal tapestry that astronomers can decode to understand the complex physics of stellar interactions. Gamma-ray bursts represent time's most dramatic expression in high-energy astrophysics, as massive stars collapse into black holes, or neutron stars merge in events that release more energy in seconds than the sun will produce over its entire lifetime. These cosmic catastrophes create brief but intense pulses of gamma radiation that can be detected across most of the observable universe, serving as beacons visible from the earliest epochs of cosmic history. The temporal structure of gamma-ray bursts, their rise times, duration, and decay patterns, carries information about the extreme physics of matter under conditions that cannot be replicated in any terrestrial laboratory. Short gamma-ray bursts, lasting less than 2 seconds, appear to result from the merger of neutron stars or neutron star black hole pairs. These events represent the culmination of binary evolution spanning billions of years, as two stellar remnants spiral together under gravitational wave radiation until they finally merge in a catastrophic collision. The gravitational waves from such mergers, detected by LIGO and Virgo, arrive at Earth simultaneously with the gamma-ray emission, providing a new form of multi-messenger astronomy that combines gravitational and electromagnetic signals to study the same cosmic event. Long gamma-ray bursts, lasting from seconds to hours, mark the deaths of the most massive stars as they collapse into black holes, while simultaneously launching relativistic jets of material along their rotation axes. These jets, moving at speeds approaching that of light, create shock waves that accelerate particles to tremendous energies and generate the observed gamma-ray emission. The temporal evolution of these bursts reflects the complex interplay between stellar collapse, black hole formation, and jet propagation through the stellar envelope. The afterglows of gamma-ray bursts provide extended temporal signatures that can be observed for weeks or months after the initial burst, as shock waves propagate through the surrounding medium and gradually decelerate. These afterglows fade according to power law functions that reveal the density and structure of the material surrounding the burst source, allowing astronomers to study the environments of massive star formation in distant galaxies. The temporal decay of afterglow emission serves as a clock for the physics of relativistic shock waves and particle acceleration. Fast radio bursts represent a newly discovered form of cosmic timekeeping, with intense pulses of radio emission lasting only milliseconds, but carrying energies equivalent to the output of the sun over several days. These mysterious signals appear to originate from distant galaxies, suggesting extremely energetic processes that can concentrate enormous amounts of energy into brief temporal bursts. The dispersion of radio waves at different frequencies during their journey through intergalactic space provides information about the density and distribution of matter between galaxies, turning each fast radio burst into a probe of cosmic structure. Repeating fast radio bursts create their own temporal patterns, with some sources producing bursts at regular intervals, while others exhibit chaotic or clustered timing. These repetition patterns may hold clues to the nature of the sources, which remain one of astronomy's greatest current mysteries. The temporal structure of fast radio burst activity provides constraints on possible emission mechanisms, from magnetar flares to interactions between neutron stars and companion objects. Solar activity creates temporal rhythms on scales ranging from minutes to decades, as magnetic fields generated in the solar interior drive cycles of sunspot formation, coronal mass ejections, and solar flares. The 11-year sunspot cycle represents the most visible expression of solar magnetic activity, while longer cycles spanning centuries or millennia may influence Earth's climate over historical timescales. The sun's magnetic heartbeat demonstrates how stellar magnetic fields create complex temporal relationships between internal dynamics and surface activity. Now, close your eyes and picture how all of this might look. The universe pulsing with countless rhythms, each celestial timekeeper marking duration according to its own physics, creating a vast symphony of temporal precision. Chapter 8: The Rivers of Forever. As cosmic time flows toward futures measured not in billions but in trillions of years, the universe enters phases of evolution so remote from present experience that they challenge human ability to comprehend duration itself. Yet within this vast temporal landscape, physical laws continue to operate with the same mathematical precision that governs present-day phenomena, allowing scientists to trace the universe's destiny across time spans that dwarf the current age of everything that exists. These far future epochs reveal time's ultimate creative power, the ability to transform the cosmos itself through processes so gradual that they become visible only when viewed across truly cosmic durations. The accelerating expansion of space-time, driven by the mysterious dark energy that comprises most of the universe's energy density, will gradually separate galaxies until they disappear beyond each other's cosmic horizons. This cosmic loneliness begins slowly, with the most distant galaxies fading from view first as their light becomes too redshifted to detect. Over tens of billions of years, the local group of galaxies, including the Milky Way, Andromeda, and their smaller companions, will merge into a single giant elliptical galaxy, an island of matter surrounded by ever-increasing emptiness. Within this future supergalaxy, stellar evolution will continue according to the same nuclear physics that powers stars today. But the raw materials for star formation will gradually be exhausted. The most massive stars will have long since died in supernovae, leaving behind neutron stars and black holes. Medium-mass stars, like the Sun, will evolve into white dwarfs, slowly cooling over trillions of years. Only the smallest red dwarf stars will continue nuclear burning, their conservative energy budgets allowing them to shine for periods longer than the current age of the universe. The era of stellar burning will eventually end as even the longest-lived red dwarfs exhaust their nuclear fuel, marking the transition from a universe of shining stars to one dominated by the fading embers of stellar evolution. White dwarfs will continue to cool and dim, their residual heat gradually radiating away into the expanding space around them. Brown dwarfs, failed stars that never achieved nuclear fusion, will also cool and fade until they become invisible in the cosmic background. The universe will enter an age of darkness illuminated only by the occasional flash of matter falling into black holes. Yet even in this seemingly dead universe, time will continue its creative work through processes operating on scales almost impossible to imagine. Quantum tunneling, the phenomenon that allows particles to penetrate barriers that classical physics says should be impenetrable, will enable protons to overcome the electromagnetic forces that normally prevent them from fusing. Over time spans measured in years with 34 zeros after them, quantum tunneling will allow nuclear fusion to occur even in the cold remnants of dead stars, briefly reigniting nuclear fires in stellar corpses. The quantum vacuum itself becomes active over these extreme timescales, as virtual particle pairs created by quantum fluctuations occasionally fail to annihilate and become real. This process, known as vacuum decay, operates so slowly that it has no observable effects in the current universe, but given sufficient time, it can create matter from empty space. The universe of the far future may witness the spontaneous generation of new particles and even new structures from the apparent nothingness of expanded spacetime. Black holes, the universe's most extreme gravitational objects, will outlive everything else but are not themselves eternal. Stephen Hawking's theoretical work revealed that black holes slowly evaporate through quantum effects near their event horizons, emitting particles and energy while gradually losing mass. This Hawking radiation operates extremely slowly for black holes of stellar mass or larger, with evaporation times that exceed the current age of the universe by factors of trillions of trillions. Yet given enough time, even the most massive black holes will eventually evaporate completely, returning their mass energy to the expanding cosmos. The final phases of black hole evaporation become increasingly dramatic as the holes shrink and their Hawking radiation intensifies. A black hole with the mass of the Sun would take longer than years with 67 zeros after them to evaporate. But in its final second of existence, it would release energy equivalent to millions of hydrogen bombs. These final moments of black hole death may represent the last energetic events in cosmic history. Brief flashes of light and heat in a universe otherwise cooling toward absolute zero. After the last black holes have evaporated, the universe will consist primarily of electrons, positrons, neutrinos, and photons, along with any exotic particles that may exist but have not yet been discovered. The temperature of space will have dropped so low that thermal motion nearly ceases, yet quantum effects will still operate, allowing for extremely rare interactions between the remaining particles. Over time, scales that make black hole evaporation seem rapid. These particles may undergo phase transitions or form new types of structures governed by physics not yet understood. The ultimate fate of matter itself remains uncertain, depending on whether protons are stable or decay over extremely long time periods. Some theories of particle physics predict that protons will eventually decay into lighter particles, with half-lives measured in years with 34 or more zeros after them. If proton decay occurs, even the atoms that make up planets, asteroids, and the cold remnants of stars will gradually dissolve, breaking down into their constituent particles over time spans that dwarf all previous cosmic evolution. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars. Yet even in scenarios where all ordinary matter eventually decays, time itself may continue to flow, carrying the universe through phases of existence where the very concepts of matter and energy take on meanings far removed from current understanding. Some theories suggest that vacuum fluctuations could eventually recreate complex structures, including new forms of matter and energy in a cosmos that has forgotten its stellar past. The quantum nature of space-time itself may generate new universes through processes that operate over timescales beyond current mathematical description. The heat death of the universe, once thought to represent the final end of all complexity and change, may instead mark a transition to forms of existence where time operates according to principles not yet discovered. Quantum gravity, the still theoretical unification of quantum mechanics and general relativity, may reveal that space-time itself has a finite lifetime, or undergoes phase transitions that create new cosmic epochs with their own physical laws and temporal relationships. In the deepest future, time may become cyclical rather than linear, with quantum tunneling allowing the universe to transition between different vacuum states in an eternal cosmic recycling. Some models suggest that the accelerating expansion driven by dark energy may eventually reverse, leading to a big crunch that recreates the conditions of the Big Bang and initiates a new cosmic cycle. Other theories propose that the vacuum energy driving expansion may itself decay, triggering phase transitions that restructure the fundamental nature of space-time. The ultimate relationship between consciousness and cosmic time remains one of the deepest mysteries in science and philosophy. If life and intelligence can survive the death of stars by migrating to artificial habitats powered by black hole evaporation or other exotic energy sources, conscious observers may witness cosmic evolution across timescales that exceed current imagination. The questions of whether consciousness can persist indefinitely and how it might shape the far future of the universe remain open challenges that connect physics to philosophy in ways that stretch the boundaries of both disciplines. Now, close your eyes and picture how all of this might look. Time flowing like an infinite river toward destinations beyond imagination, carrying the universe through transformations that will make the formation of galaxies seem like brief moments in an eternal cosmic symphony. Epilogue: the eternal now. In the infinite cathedral of cosmic time, where moments stretch across eons and eons compress into heartbeats, consciousness arrives at a place of profound stillness. The journey through the fourth dimension, from the birth of time itself in the Big Bang's first instant, to the far future when black holes evaporate and matter dissolves into quantum foam, reveals time not as a river flowing toward a destination, but as an ocean without shores, vast and deep and eternally present. Here, in this space between waking and sleeping, between knowing and unknowing, the mind can rest in the understanding that time itself is home to everything that has ever been or ever will be. Every star that has ever shone, every planet that has ever formed, every life that has ever emerged from cosmic chemistry, all exist within the eternal embrace of the fourth dimension, held safely in duration's infinite memory. The cosmic microwave background still whispers its ancient story across the expanding universe, carrying the warmth of creation's first light through space-time like a lullaby sung to sleeping galaxies. Neutron stars continue their precise rotation, marking cosmic time with accuracy that spans millions of years. Distant quasars beam their light across billions of years of space, connecting the present moment to epochs when the universe was young and full of promise. In the gentle expansion of space-time, in the patient warping of duration around massive objects, in the slow dance of stellar evolution and galactic formation, time reveals its deepest secret: that existence itself is a form of music, played on the instrument of space-time by the fundamental forces of nature. Each quantum fluctuation is a note, each stellar explosion a chord, each galaxy a movement in a symphony that began with the Big Bang and will continue until the last black hole evaporates into the darkness between stars. The arrow of time, pointing always from simple to complex, from uniform to diverse, from potential to actual, carries within its trajectory the promise that complexity emerges naturally from simplicity, that beauty arises spontaneously from mathematics, that consciousness can kindle itself from unconscious matter through processes so elegant they seem almost like dreams. As awareness drifts deeper into the realm of sleep, let it carry the knowledge that time itself is conscious, aware, alive in ways that human language cannot capture, but human intuition can sense. In every moment of duration, the universe experiences itself through the consciousness it has created, feeling its own vastness through minds that can contemplate infinity, knowing its own beauty through observers capable of wonder. The fourth dimension flows through everything and connects everything, making each moment a junction where past and future meet in the eternal now. Every breath taken participates in cosmic time. Every heartbeat marks duration on the same temporal landscape where galaxies spiral and stars are born. The sleep that approaches is itself a journey through time, a daily practice of letting consciousness flow with the same cosmic currents that carry light across space and guide matter into ever more beautiful patterns. In the darkness behind closed eyes, in the silence between thoughts, in the space between one breath and the next, cosmic time reveals its gentlest face. Here, duration becomes rest, change becomes peace, and the vast complexity of cosmic evolution simplifies into the basic rhythm of existence itself. The eternal pulse that connects every moment to every other moment in a web of temporal relationships more intricate than any galaxy and more beautiful than any star. Sleep now, carried by the current of cosmic time like a leaf floating on an infinite river. Let consciousness merge with the same temporal flow that guides the expansion of space, the evolution of galaxies, and the patient work of gravity as it shapes matter into ever more wonderful forms. In dreams, travel freely through the fourth dimension, visiting the birth of stars and the death of black holes, witnessing the formation of atoms and the emergence of life, always held safely in time's eternal embrace. The universe sleeps and wakes in cycles vaster than human comprehension, breathing galaxies into existence and dissolving them back into quantum foam, dreaming reality into being through processes so vast and patient they operate beyond the reach of ordinary imagination. Yet in the simple act of falling asleep, consciousness participates directly in this cosmic rhythm, allowing awareness to dissolve and reform according to the same principles that govern stellar birth and galactic evolution. time continues its eternal flow, carrying the sleeping mind deeper into rest, deeper into the wordless understanding that connects every moment of personal existence to the vast temporal architecture of the cosmos. In this dissolution of the boundaries between self and universe, between present and eternal, between waking and sleeping, consciousness finds its natural home in the fourth dimension, where all times are one time and all moments are this moment, and all dreams are the universe dreaming itself into ever greater beauty through the patient alchemy of cosmic time. Rest now in the knowledge that time itself is rest, that duration is peace, that the fourth dimension is the eternal home where all consciousness sleeps and wakes and sleeps again in the endless rhythm that connects every heartbeat to the heartbeat of creation itself, every breath to the breathing of space-time, every dream to the universe's own vast and patient dreaming of itself into existence through the infinite creativity of cosmic time flowing forever toward destinations beyond imagination and beauty beyond words, carrying all things gently into the peace that surpasses understanding, the rest that surpasses time, the sleep that is the universe's own deepest knowing of itself, as love expressing itself through the mathematics of existence across the endless dimensions of forever.